thank you all for joining. I'm very happy to animate this space. Yeah, we have on the same space the creator of Ethereum, the creator of stocks, and the creator of Cairo. So this is very exciting. First, I will ask you a simple question about naming and branding. Should we say ZK rollups or validity rollups? It's a quite hot topic, and we started with the term ZK rollups, but actually we should probably say more validity rollups. Do you think it's important to have clear names? Do you think it's too late to change that, or yeah?
No, and I'm happy to use whatever name that you want to use here. So if we want to call them validity rollups, then sure.
Okay, great.
I mean, for the purposes of, I always say this, I just have a problem with, the mathematician in me has a problem with calling ZK things that aren't. It's like saying, 10 is a prime number to mean that it's a really, really good number. It's a really good number. I love 10. I can work with it.
Can you expand, Eli, on what is your concern about that, and what is the risk of calling those with the wrong term?
It's something I face regularly, is that if you call it ZK is very much related to privacy. So the next question is, okay, explain what ZK is, and then explain how it helps to the matter at hand. And then first of all, you have to say, well, it's not really ZK, and ZK is about privacy, So I get detracted, and I just prefer to get straight to the point, which is this is about scaling and so on and so forth. And one way to avoid it is not to call it something that it isn't. By the way, Aztec, which is an amazing team, they are doing a ZK rollup in the sense of zero knowledge and privacy. So I think it's also unfair to them. They are a ZK rollup. Maybe probably the only ZK rollup I'm aware of. So I don't want to take their thunder.
Good point. Okay. So yeah, today we are going to talk about proving systems, and specifically about execution engines and the different types of the execution engine. So we'll talk about ZK EVM execution engines, but also non-ZK EVM, because obviously, as you all know, Starkware is working on non-ZK EVM execution engines. And we will talk about the reasons about that. And also we will talk about a new community project, which is called Kakarot, which is a ZK EVM written in Cairo. So we will talk about that. So the first thing I wanted to cover is Vitalik, in your article about the different types of ZK EVM, you mentioned that Ethereum was not initially designed to be ZK friendly. So can you expand on that, and can you basically tell us a bit more about the parts that are not friendly, efficient to prove on Ethereum?
Sure. So when Ethereum started, the whole concept of ZK Synarchs and that whole space was just not on almost anyone's minds in the group. In the crypto space, right? Actually, I remember visiting Haifa in Israel and interviewing Eli because I was doing Bitcoin Magazine then. So it's literally 2 months before the Ethereum project started, and that's where he explained some things about Synarchs, and I think tried to explain a bit about the precursor to Starks at the time. And at the time when I heard these things, they seemed amazing, but this seemed like this, still extremely speculative, very early stage moon math that would take potentially decades to get to the point where it's actually something that we can use, right? And so it was at the time, it just felt like this far away future thing. And so the EVM was not really designed with any kind of friendliness toward Synarchs or Starks or zero knowledge, anything in mind. And as a result, there are just a lot of components in it that are basically just accidentally very ZK unfriendly. So I guess it's just to kind of very briefly go into what it means for something to be ZK friendly and ZK unfriendly, right? So Synarchs and Starks, they work over a type of math that, or usually that's called that's called finite field arithmetic, right? Where it's basic, where you generally done through like you know addition and multiplication modulo some prime number, right? So it's like basically clock arithmetic, right? So like if your modulus is 11, then like 4 plus 5 is 9, 5 plus 5 is 10, but then 5 plus 6 wraps around to 0 again. And modular arithmetic is really nice for cryptography because it lets you do adding, multiplying, and lots of operations, but whatever results you get, the result is still going to be a small number in the same in the same size, right? Which turns out to be really important, especially for these kinds of applications. And so if you can express the computations that you want to make through the prime field modular arithmetic directly, then you can generally make things that are pretty friendly and efficient to these constructions. But the problem is that a lot the existing cryptography that Ethereum relies on doesn't really work that way at all, right? So hash functions, for example, like things like SHA-256 and SHA-3 or Kachak, these rely on a lot of bit operations, and they rely on bit operations that are like very specifically chosen to be very friendly toward what existing CPUs are capable of doing quickly, right? So like CPUs make a lot of assumptions about stuff being 32 bits, 60 or 64 bits, and doing bit operations that like do the same thing to many bits in parallel, and you have ands, ors, and shifts, and these are all things that are totally not naturally translatable into modular arithmetic, right? In order to translate them into modular arithmetic, you have to get pretty close to like just decomposing everything into zeros and ones and logic gates. And even though you have these big field elements that are all 256 bits big, you basically only use one of those 256 bits. And so there's just like a lot of this inefficiency that in practice makes the EVM much more expensive to prove than a VM designed with the idea of proving in mind would be or could be designed to be easy to prove. And so people, and then that was aside from things like hashes, and then there's other things like the way that's the signature schemes. There's the Merkle-Patricia tree. There's like which specific moduluses are used, right? Because like it can't be modular arithmetic in general. You have to kind of pick a specific one and stick to it. And there's just all of these different considerations because of which the EVM doesn't really line up to like what Starks and Starks require. And if it did, then things would obviously be much more efficient. Or because it doesn't, you just have to like use a lot of complicated tricks and incur a lot of overhead and just pay a lot of costs and pay a lot of complexity in order to be able to ZK prove EVM execution. But of course, the fascinating thing is that we've had multiple teams like go ahead and actually do the really hard work and do it. And the result is that you get these EVM provers that can make proofs of EVM execution. And so if you do that, then you add a little bit more work. Basically, it could be used to prove at least the execution side. So not the consensus side and the proof of stake signatures, but just the execution side of the transactions of existing Ethereum blocks today. I don't think anyone's like 100% at that level yet, but people are getting closer and closer. And again, the numbers that I've seen so far are still far from being fast enough for most things, right? Like potentially it might take 12 hours to prove an Ethereum block or something close to that. And so that actually can still be useful for rollups if you come up with a rollup or you do some clever thing where you add proofs after the fact instead of proving in real time. But we're still quite far away from being able to prove in real time, which is something that would be needed if we want to, like, say, use these Snarks or Starks to make the blocks in the existing Ethereum layer 1 chain provable, so people will not have to, or even people running clients would not have to actually run the execution themselves, right? So, yeah, like basically just like a bunch of different choices in terms of mostly the cryptography that the EVM uses, but also a couple of other things like the fact that memory is based on bytes, and that you grab 32 bytes at a time, and you can grab 32 bytes from anywhere, including from like the middle of a 32 byte range, and just all of these decisions that really increase the number of what are called constraints. So, like basically the number of sort of the ZK proof systems equivalent of computational steps that have to be made to actually prove execution.
Okay, thank you for this explanation. And basically, those parts that are not ZK friendly are very important in the different types of ZK EVM, because those are the parts where some projects are doing some trade-off and they decide to switch from something that is not ZK friendly to something that is ZK friendly. But we will talk about that later. Then the next question is for Eli, and you already gave some part of the explanation, Vitalik. What was the reason initially when you started to not go through a ZK EVM idea initially, Eli, when back in the time after the creation of Starks, etc.?
So first of all, I just want to say that I still remember very fondly sitting the meeting that Vitalik that you mentioned. That indeed we had. What I mostly remember is that we had the hummus at the university I was at the time at Technion, and we're chatting about a whole bunch of things. It's so amazing to see that several years later, you actually went and created this amazing thing that is Ethereum with it. I remember like discussing the bounded halting problem, and of course also proof systems. But anyways, that was a long time ago. So when we started dabbling with generating validity proofs for the purposes of scaling, it was a very daunting prospect, because there's a lot of complexity that goes on into generating these proofs, and complexity in two ways. One is complexity in taking a computation and turning it into a system of constraints that captures the computation. And here, maybe for the listeners, I think a good analogy is you probably all saw those pictures of, von Neumann and other early advents of computers who were basically, looking at these switchboards with, or whatever it was, vacuum tubes or something, and connecting them by these like huge systems of wires and so on. So I think it's something like that. You, for the first time, try to take any sort of computation and put it in this model. In our case, it was generating a proof for it. And we started with relatively simple computations, and we wired things by hand. In our world, it means writing polynomial constraints for these things, but that's the analog. And that was what we felt comfortable with. And then the next stage was that some very brilliant folks, Shachar and Lior and others, said, we have something that is maybe just a little bit more complex, or actually perhaps even simpler. But it's a very minimalistic set of wires or polynomials that nevertheless captures something like a CPU. And because we still were worried about the complexity of how efficient generating proofs might be. We said, this is something relatively simple, but it's good enough to start writing programs and writing computations in this framework, which is Cairo. And that's how we got to Cairo. So it really came out of this realization, this very conservative approach of trying to take one step at a time. At the time, we didn't think necessarily that we'll have StarkNet or open it up to the rest of the world. This was just an attempt to make things easier and make the development more secure and more scalable. And that's really how we ended up with Cairo. So we didn't have this aspiration to take all of Ethereum existing Solidity code or things like that. It was just, let's make it easier for ourselves to build systems like the ones for DYDX or Sorare or Immutable. Let's just make it simpler for us to add functionality. So that's literally how we came across Cairo.
Okay, very cool. To expand more on that, usually when we talk about proving systems, we say, okay, there is a prover and there is a verifier, and the prover wants to prove a statement to the verifier. But I think it's very abstract for people to know how you go from a concrete statement like I want to transfer X tokens to something that is provable. And Shah, I would love to have your perspective from someone who was writing those polynomial constraints manually back in the time, and like to expand and to detail what Eli was saying, what led to the creation of Cairo and the different steps that led to the creation of Cairo.
Sure thing. Well, at the beginning, like Eli said, we had the Stark protocol, and the way you describe a statement, the Stark protocol, is using polynomial constraints. Basically, just equations that describe some relations. For example, if I want to do the Fibonacci, I would say something like Z equals X plus Y, and do that a repeated number of steps. Now, for Fibonacci, it's very easy to make complex statements. It's kind of hard to manually design these polynomial constraints and do it efficiently. At the beginning, the first product we actually did something interesting for was StarkX, which was basically supporting transfers, deposit, and settlements. And we designed an error, and it was nice. We had even a framework to help us design errors, which made things a little better. But
I think no one knows what an error is. Maybe you want to just...
No one knows what an error is? Yeah. The error is just the set of polynomial constraints. Yeah, should have mentioned that. The set of variables we have and the polynomial constraints on top of it. So we had a framework to help us build this in maybe a bit more abstract way to describe variables and relations between them. But it was very hard to make changes and make complex things, and even optimization that would have been possible in regular programs was very hard to express it in polynomials. So we knew we needed something better for this. And one option was maybe writing some kind of a bit high-level language that will compile to polynomials, which is something that was happening around. There were other languages that did it for snarks, but at the end we decided against it. If we wanted to do equations, we had our framework, which was good, but we wanted to go toward something we regarded as the holy grail. If we could have something for general computation like a CPU Now, if we consider the manual design of polynomials as designing chips, designing circuits, then the whole grail would be like CPUs, a way to have some reduced instruction set and have the specific polynomial, just one polynomial set verifies it. And once we do, we'd have a bunch of benefits. We could write in really high level languages, but without the drawbacks of compiler to polynomials. Just if any of you ever programmed in one of those languages, you can't do recursion, you can't do arbitrary loops, only just like a specific number of steps, and you can't, it's not Turing complete. However, if you are doing the Holy Grail approach, having this kind of CPU, then you could do everything of this. You could have real high-level languages. You could compile from maybe EVM, for example, or x86, or maybe something else. And so we spent a lot of time to research and all kinds of designs. And we did have a specific goal to make it as efficient as possible, because we knew the benefit and maybe the biggest advantage of Stark's or technology was that it is very scalable and fast to prove, and we wanted to double down on that. So we wanted to be fast and easy to prove. So we made a lot of decisions, for example, using immutable memory, using basic field elements, and efficient ways to communicate with what we call built-ins, but to add some additional capabilities on top of the basic air. And those made the polynomial set that verifies the VM that we called Cairo very efficient. So when we came out with Cairo, the first users of this was us, was Starkware. In the beginning, we didn't really think about making it public for other people. We didn't even think about Starknet. It was just for us to use internally to help us write better applications. And it did. It was a real game changer when we rewrote StarkX using Cairo. It was a lot easier, and we did a bunch of very cool optimizations that, even though you would think that it would be less efficient to write on top of this, because when going from ASICs, from circuits to CPU, there is an overhead. ASICs are obviously more efficient. But in this case, moving to a ZK CPU allowed us to add a bunch of optimizations that were very, very difficult, maybe even not possible, in the old approach. So we even got additional scaling and benefits when we wrote our applications on top of Cairo. And at the beginning, Cairo was very assembly-like, which is, it's good and bad. It allows you to do some very low-level things if you want to be efficient, but even though it's a lot better than writing polynomials, it can be a lot harder to do other stuff. Well, I guess I'll talk about it a bit later, but this was generally how Cairo was created and why.
Okay, very cool. Yeah, I guess we can start to talk more about the different type of ZK EVM. So maybe with Vitalik, you can give a brief overview of the different types and the different trade-offs. And yeah, we can talk about more stuff later. Vitalik? Are you with us? Okay.
Yeah. I'm here. Yes.
Okay.
Yes.
Yeah, I was asking, basically, can you give a brief overview of the different types of ZK EVM?
Sure. So I think like there's different ways to look at the different kinds of ZK EVMs that are being made, but the categorization that I made in my post is to basically look at the trade-off between being more similar to the existing EVM versus making more modifications generally in order to be more ZK friendly, right? So the four types that I had, one is type 1, which is basically a perfect replication of the Ethereum execution layer, even to the point where you would be able to feed Ethereum blocks into it and it would verify them. So this is like maximum compatibility and but at the same time maximum challenge and maximum overhead because you have to deal with not just stuff inside the virtual machine, but also hashes and DSA signatures and a whole bunch of things. Then there is type 2, and type 2 is a fully faithful ZK EVM, but not a ZK Ethereum. So the difference is that parts of Ethereum execution that I would consider to be not part of the virtual machine, so particularly things like how the state tree is hashed and like how transactions are hashed and possibly how transaction signatures work would not be included in that. And so you'd be able to swap those out and replace them with something much more ZK friendly to make it easier to implement and reduce constraint count. But at the same time, type 2 still preserves full EVM compatibility, right? So any EVM unit tests would still run the exact same way, and any application that works on one would run on the other unless it depends on like some kind of like weird history introspection, which there are like Merkle proofs that are rooted in some historical block hash or something, and there are definitely a couple of apps that do that, and those would break under anything except for a type 1 ZK EVM. A type 3 ZK EVM is willing to break even more things. So it's willing to accept a small level of incompatibility. So it could have different hash functions to generate addresses. Maybe you could not include particular opcodes or particular precompiles that are too difficult to implement. Like if it makes changes that are incompatible in order to reduce the complexity for developers or for reduce constraint count, then becomes type 3. And then type 4 isn't even a ZK EVM. It's like what I called a ZK Solidity, right? Or a ZK some other environment that compiles down to EVM, but where EVM can't compile to it, right? So it's kind of strictly above the EVM and sort of the DAG of like what can compile to what. So type 4 ZK VMs can be even faster and both faster to execute with a low constraint count and easier to implement, right? And Matter Labs is taking a type 4 approach, and they are further ahead of the type 1, 2, and 3 teams so far by a pretty significant margin. But at the same time, it comes with the sacrifice, which is that there's just even more tooling that doesn't work, and a lot of things that would work with an EVM end up not working with that kind of approach, right? So if you do a ZK Solidity, then the next question is like, can it support Viper or other high level languages? And I believe like Matter Labs' type 4 ZK VM, for example, can support Viper because there is now a compiler that goes through some assembly, which happens to be one that Solidity supports. But it's like it gets complicated, right? And
Yeah.
So like that's the trade-off. Yeah, like basically, the lower the types go, the more it's easier for a kind of end developers and people building things on top of it. And the higher the types go, then on the other end, the easier it is to build and run the thing itself.
Yeah, right. To give another example of type 4 ZK EVM, we can mention WARP from Nethermind team, which is building basically a transpiler from Solidity to Cairo. But as you said, Vitalik, it's very specific because it can only go from Solidity and not Viper, for example. But still, I think like this variety of different types is good because it can fit for different needs for different projects. And depending on what is important for your project, you can choose between all those different types. Like if you want maximal efficiency, you don't have the same need in terms of tooling compatibility and whatnot. So yeah, I think definitely that this variety of choice is very important. So to give a few words about Cairo and the fact that it is a very powerful tool to build some programs that are computationally verifiable. The fact that we started like this community project, which is called Kakarot, and the idea is to build an entire EVM fully written in Cairo. And like we started something like 3 weeks ago, and we already implemented 109 opcodes on the 142 opcodes that exist on the EVM. And we can do that just because of the power of Cairo and the fact that you can build arbitrary and general purpose computation. So I think this is a very good showcase of what you can build with Cairo, because if you are able to build even complex stuff like an EVM in Cairo, like you can build almost everything. And Cairo is not even in its final form. And so, Shah, maybe you can give a brief overview of the upcoming changes, and especially Cairo 1.0 and Sierra, and the fact like that we will be able to prove invalid transactions, which is a big thing. Like, can you explain more about the upcoming changes?
Yes, of course. Well, we're like I just mentioned, Cairo at the beginning or even currently is very close to low level instructions. That's what we had at the beginning, and we want to change that. We want to make Cairo a lot easier for developers to use. That is the main reason of coming up with Cairo 1.0. For example, currently Cairo doesn't have for loops. You need to use recursion. Cairo 1.0 will also need to work through recursion because that's how the virtual machine works. But users shouldn't see that, and they won't. They'll just have loops, and it will compile down to whatever. Also, Cairo 1.0 will solve all the variable issues that exist with Cairo. It will be safe. It will have a lot of nice high-level features and good start library. It will have good package manager. So basically, and also safe arithmetic by default, and very easy to use other arithmetic types, not just field element, but you could use uint, uint 256s, basically everything that will help the developer have a nice time, make it a fun language to write it. That is the main focus of Cairo 1.0. We are at it for like 3-4 months right now, and expected to finish this in a few months. And the second major thing about this release is Sierra, which is a way to enable proving failed transactions. The other issue today with Starknet, which is our layer 2 that uses Cairo as the basic machine, you can't prove failed transactions because failed transactions in Cairo VM mean you can't prove this. If you do assert 1 equals 2, you can't make a proof of it, which is actually a feature. This is what makes this zero knowledge system sound. However, it means that if your program has this assert, you can't prove it, and it means it's hard to collect fees for virtual transactions, and it means it's very hard to do anti-censorship, maybe forced transactions. And so Sierra comes to solve it. It's an intermediate representation, something that is more low level than the high level language, but it's a bit higher level than Cairo VM itself. And it will be safe in the sense that any program written in Sierra bytecode, in this intermediate representation, cannot fail. You can't write anything that fails. And this reverted transactions will actually be transformed into programs that return false instead of failing. And this in Cairo 1.0 will compile down to Sierra. Then you will take the Sierra bytecode and deploy it onto StarkNet. And in the last phase, StarkNet will translate it from Sierra down to Cairo VM to make it also more efficient. So yeah, these are the main changes that are coming.
Okay, very cool. So are you saying me that we should have waited Cairo 1.0 before starting to write the EVM? It would have been much more easy, right?
Yeah, I mean, yes and no. It will be easier, but the work done right now won't go to waste. We plan to have very good backward compatibility and migration tools to help you move from today's Cairo 0 to Cairo 1.0. So you shouldn't be afraid.
Okay. Awesome. Let's talk about Kakarot and the architecture and what type of ZK EVM it is. So for the moment, we design it as a smart contract on StarkNet, and this is very funny. Actually, it's a kind of inception, because in a smart contract on StarkNet, you can run a full EVM. And run a bytecode program from Ethereum. So we aim for bytecode equivalence, but for the moment we can consider it something like more type 3, because very likely we will do some changes to the hash functions and maybe also to the precompiles. And like I really liked Vitalik in the post, like you mentioned, that it can be an incremental process, basically, where a project can start with a type 3 and then do some modification and become more and more compatible. Can you explain more about your vision about that, basically how a project could start with a lower type and then do some modification to be more compatible with Ethereum tooling?
Yeah, no, it's definitely a good point there. I think in general, like all of the ZK EVMs that I'm following, right, like they want to get somewhere, right? Like software developers, they don't want to like spend 2 or 4 years of working on a thing and feel like they have nothing to show for it all the way right up until the end, where they have some amazing thing, because they could just burn out before they even get there, right? And which it's fair to make, and it makes a lot of sense, and it even makes a lot of give a business sense for these organizations to be able to hit the ground running with something early. And so the path that they often end up taking is start off building a ZK VM for whether it's for a validity rollup or for some other thing that they're doing. And then, but at the beginning, if they find any parts of the existing EVM that are too hard, you just skip over them, right? So like a lot of them, they skip over pre-compiles, like the BN128 pairing precompile in particular, because doing pairings inside of a circuit is just like devilishly hard. Potentially, some hash functions, replace SHA-256 with Poseidon or some other fairly simple thing, and just a long list of simplifications, and probably just like some differences in behavior that are kind of even more accidental than anything else, right? And then over time, once that code base solidifies, then at the same time, they start kind of polishing the edges and working on the discrepancies between their ZK EVM and the existing EVM and just fixing them one by one, right? And so I think the thing that makes sense to do there is to first make sure you have full EVM compatibility, just because once you get EVM compatibility, there's like a lot of developer tooling and a lot of other nice things that you can unlock. And then after that, start also moving into replacing the tree structure and the block hashing and state hashing and all of that, and start moving toward. So first, I'm going to move toward type 2, and then move toward type 1. And one interesting thing that you could do is once you do that, you could also add you could basically make EVM compatibility be a switch that you can toggle, right? Because if you want EVM compatibility because you're actually verifying Ethereum blocks, or you just like really need total infrastructure compatibility or whatever, then like fine, you just turn on that switch and you do that. But then if you want to use that same role ZK EVM for some validity rollup where it's not as important to kind of technically be possible to just directly push your rollup blocks into Geth and have them validate or whatever, then if you instead turn that function off and you use let's say efficient or Stark friendly hash functions instead of regular hash functions, then that lets you save a huge amount on constraints and on proving time, which just makes your entire project significantly faster. Like you might be able to verify Ethereum blocks in 4 hours instead of 12, or potentially even less or whatever, right? One other interesting gray area, by the way, is gas costs, right? So gas costs in the existing EVM are set based on the time approximately that it takes to just execute that particular operation on an average piece of hardware. And there's obviously many different kinds of hardware, and sometimes different things are faster on different pieces of hardware, but just like taking an average. But because Synarchs are such a fundamentally different environment, you can't the kinds of things that are fast and slow are just going to be wildly different, right? So like hash functions, as I mentioned, are one great example, right? Like SHA-256 and CAD-SHAG, like those are very fast on a computer, but they're very slow inside a proof. But on the other hand, like S-load, for example, just like grabbing storage, that's going to be expensive on a regular machine because you have to do I/O, but it's potentially going to be fast inside of a proof, right? So the other thing that you could do is you could make a toggle switch for like basically, are you kind of faithfully using Ethereum's gas costs, or are you going to kind of plug in your own gas costs instead? And I think I might have even used the word type 2.5 for like a compatible VM that changes gas costs around. But ultimately, I expect even the consensus layer EVM itself to change its gas costs quite a bit in response to all of this stuff. So it is a pretty temporary thing, right? But in the meantime, you start kind of being very different, so then you get toward more and more compatibility. And then I think even after that you could even have some options for both compatibility and incompatibility if you value speed in particular cases, and you just choose depending on the application.
Yeah. Okay. Are you saying that we can even see some dynamic ZK VMs that could choose the type of compatibility based on some configuration, something like that?
Yeah, exactly.
Okay. Very interesting. Yeah. Okay. I have an important question for you, Vitalik. Have you started to learn Cairo or not yet?
I have I have not done Cairo coding yet, but I have read through the tutorial and quite a bit of the documentation.
Okay, very cool. Okay. Once you are ready, I'm waiting for your pull request on Kakao.
Perfect. I will keep that in mind.
Yeah.